Scientific notation is useful when dealing with very big or very small numbers. You see it a lot in, for instance, chemistry, physics, astronomy, astrophysics, things like that, where you're dealing with super large scale, super small scale. What does it look like? Let's just write down some examples. I don't know, 3.792 times 10 to the 14. I'm just making this up, but that's what it looks like. Let's do maybe 2.37 times 10 to the negative fifth, right? These are in what we call scientific notation. Here's the general form. It goes like this. It goes, you put one digit here, point, whatever you need after that, times 10 to the something. Okay, and then let's see here. So this first thing is one digit. Okay, so it's 0 to 9. It's actually 1 to 9. Between 1 and 9, you wouldn't have 0 here. And up here, you just have an integer. Remember that integers are the positive and negative whole numbers. Okay, so let's see how it works. All right, let's take a nice example like 80. We want to convert to scientific notation. Convert to scientific notation. Okay. 80. The way you do it is you take the decimal, which is out here, right? Anytime you have a number, there's always a hidden decimal at the end of it there, and we pop it 1 this way. Right? That gives us 8.0, but since we moved it one place here, we write it as 8.0 times 10 to the 1. Okay, we moved this decimal one place to the left, so this number got smaller, 80 became 8, and so this number, we didn't have any 10 before, now it's 10 to the 1, that became larger. Technically it was 10 to the 0 before. Okay, well, does this work? Yeah, check it out. This is really just 8 times 10 to the 1. 8 times 10 is indeed 80. Check, and that's what we have. So 80 in scientific notation is 8 times 10 to the 1. All right, we're just warming up here. We wouldn't really write 80 in scientific notation because it's not much of a shorthand. It's actually much longer. Let's try another one. Let's try 800. Okay, we take our decimal. We want to write this in scientific notation, so it's going to be some digit times 10 to the something. So 1, 2. Okay, we moved it 2 to the left. Right, so that gives us 1, 2. It's still 8, or you could write it as 8.00. For our purposes, you just write it as 8. But in chemistry, it would matter. In physics, you can write 8.00 as well. Times 10 to the, well, 2, because we moved it 2 places to the left. All right, just to check and make sure we're doing this right, 8 times 10 to the power of 2, well, that is 8 times 10 to the power of 2 is 100, which indeed is 800. Okay, so that's essentially how it works. Let's try one where we might actually want to write it in scientific notation. Let's do 9,300,000,000. So 9,300,000,000. Okay, 9,300,000,000. Right, that's a lot of zeros. So we don't want to write all those. So we'd convert this into scientific notation. I'm taking my decimal here. 1, 2, 3, 4, 5, 6, 7, 8, 9. That was 9 places to the left. All right, so then this number must be 9.3 times 10 to the 9th. Scientific notation. Actually, it's a much better way of representing it. Especially once you start using this, you start to recognize things like 10 to the 6 is always million. 10 to the 9 is always billion. So the more that scientists work with this notation, the more they start to internalize what it actually means and get a feel for the scale of these numbers. Let's see how scientific notation works for really small numbers. Okay, so we might have something like 0.8. All right, that's not quite in scientific notation. For it to be in scientific notation, we have to have one digit to the left of the decimal, always. Okay, so I'm going to move this decimal one place over here to the right, and this then becomes 8 times 10 to the negative 1, right? My 0.8 became 8, so that got bigger. There's a lot of balancing that goes on here. So this here has to get smaller. It's the same number. By making it bigger, what we added here to make it 8, we have to take off over here with the negative 1. Okay? And does that work? Yeah, let's check it out. Well, this is really just 8 times 10 to the negative 1 is 0.1, right? You can look at that as 10 to the negative 1 is actually 1 over 10, which is indeed 0.1. But 8 times 0.1 is indeed 0.8. So that works out. All right, so right here is our scientific notation. 8 times 10 to the negative 1. All right, that's an example. Let's try another example. And again, we're just getting our feet wet here. So we're starting a little bit simple just to make sure we have the method down. So let's try 0.08. Okay. Let's see here. 1, 2. This is 2 places over. This was 1 place over. All right, so that gives us 8 times 10 to the negative 2. Right? This number got bigger. 0.08 became 8. That's bigger. So then this number up here is negative. It gets us smaller. So 8 times 10 to the negative 2. There we go. And just to verify that it works again, let's do, does it work? Well, 8 times 10 to the negative 2 is 1 over 100, which is 8 times 0.01, which indeed is 0.08. So it works. It'll always work. You don't have to check it every time. I guarantee you it'll work if you're doing it correctly. Okay, so let's try one where we might actually use it in the sciences. Okay, we wouldn't write 0.8 or 0.08 in scientific notation like that, usually. But we might write something like this in scientific notation. Let's do 0.000000017. Okay, that's a lot of zeros, and that number is pretty hard to conceptualize. I just see a bunch of zeros, it's small. Okay, so let's convert that to scientific notation. 1, 2, 3, 4, 5, 6, 7. We do it until there's 1 digit to the left of the decimal. All right, so 1.7 times 10 to the negative 7. Right, this number got bigger. That really small number became 1.7, so then we have to take that back off with this negative exponent. There we are.